Okay, so we're picking up from the problem that we started with yesterday, and due to yesterday's fire drill during this class, it's interesting. All right, so we were picking up here. So decomposition of salt and water. So this is actually it's dissolving, so therefore it makes it decay. So it's going away. Okay, so it should be going down. If it's decaying, it should be going down, right? Okay, so growth, it should be going up, right? Make sense? Okay, good. Okay, so we went over this, so I'm going to review this a little bit from yesterday. So my initial amount was right here, A sub naught, my 25 kilograms of salt. Okay, my initial time is 0 hours. The time that I gave it was 10 hours, and at 10 hours, I had 15 kilograms of salt. Now, this is algebra here. It's algebra. So what I did is, I showed you why it came out like this. Okay, initial 25. Then I plugged in my initial amount, which was my A sub naught, into my formula over here, the initial amount here, and then I plugged in my times for this. So this is my 15 that I have after 10 hours. And right here, this is my 10 hours. My T is 10, and then my salt is there. So now we divided both sides by 25 to try and get that by itself. Okay, I came out with reducing the 15 over 25. Sorry, my board's restarting. 3 over 5 equals e to the 10k. So now this is an ln rule, so it is a natural log. So to undo an e, we ln both sides right here. We ln both sides. So that's going to cancel out my e, so I'm going to be left with the 10k. So I'm left with the 10k there. So ln of 3 over 5, okay, divide by 10 to get k by itself, because I needed a value for k. I have to have that value. That is the rate of decay. The rate of decay. This is my rate of decay. So now, I'm going to take this. In AP Calculus, you're always going to round 3 decimal points. Always 3. Okay? On the AP test, they grade you on it being 3 decimal points. Okay? Even if you have the right answer, you have to have 3. Okay? Even if you just left off that last one. Okay? You have to have 3 here. So, next page right here. Actually, I'm going to back it up first. So, let's back this up, and it says, okay, we found, okay, right here, for part A, so we found our equation. We have our K, we have our T, we have everything we need. So, part A says, how much, it says, how much undissolved salt is left after 1 day. So, what is that new information? 24 hours. Since my T is in hours, right? So I know that T has to be 24, and I'm looking for A of 24, right? I'm looking for that value. So I'm going to plug this in. So now if it's A of 24, what goes next? A sub naught. What was the A sub naught here? 25. That is my initial amount. So 25 e to the, okay, so yeah, I have my negative 0.051 times 24, which is my t value. Now, do I have any variables on the right-hand side? Say no. No. So since I don't have any variables, what do I do now? Just plug this in, right? Just plug it in. Plug it into your calculator now, please. So everyone's plugging it into the calculator. So
7.351.
3.5 what? 3.51?
Yes. 1.
1. What are my units? Kilograms. And what is the kilograms of? Salt, sodium, right? Okay. There it is. We solved for A. That was all part of A. Because you have to set up your function, you have to know your K, you have to know all those things. Okay, we have all that, so that's going to make the rest of this easy. So, part B says, how long will it take until 12 kilograms of undissolved salt remains. Okay, so now, what information is it giving me this time? It gives me the A of t, right? And then what am I supposed to be solving for? The t. Very good. So now I have 12. So now the next one says 12 is going to be equal to 25, which is my initial amount, e to the negative 0.051 times t, right? Right there. Okay, algebra now. What do I got to do? My variable's up here, so I start by doing what? Divide both sides by 25, right? So we're dividing both sides by 25 to get this by itself first. So if I divide by 25, I'm going to do the reducing also. So 25. So 12 over 25 gives me what? Can I reduce that? No, not really. So it's going to be 12 over 25 equals e to the negative 0.051 t. ln both sides. Okay, you're lnning both sides. So it's ln here and ln here, right? So when I ln the e, that goes away. So now I'm going to have ln of 12 over 25 is equal to negative 0.051 t. Then divide by that. Let's go ahead and divide by that. Negative 0.051. Negative 0.051. So you could say t is going to be about, calculate.
It says non-real.
14 point what?
Oh, it has to be a radian. Huh?
No. 14 point what?
392, right? Yeah,
392. And what are my units here?
Time, right? So it's hours.
Hours. Very good. Okay.
It wasn't radian. Oh, because that's inside the ln, that's why.
Oh, got you.
Okay.
It should be ln at the top.
Yeah. So let me see, start this over again. Then right here, control divide on the outside. There we
Oh,
go.
okay.
Okay.
Thank you.
All right. So we got that. Okay. So that's how long it's going to be when I have 12, right?
Yeah.
Okay. Oh. Okay, so we got that. Okay, that one's done. Find the limit as t approaches infinity of a of t. Okay, look at the values that I have already. So at 10 hours I have 15, right? So I start off at 25, 10 hours I have 15. At 14 hours I have 12. At 24 hours I have 7. What do you think this is doing as a of t approaches infinity? It should go down to 0, right? This is a decay, isn't it? It's a decay. So over the time, over a long enough span of time, this is eventually going to go down to 0, right? So it's eventually, it keeps going down. So it starts, so if I had a curved graph for this, it would look something like this, right? So it's eventually getting down to 0. Just slowly and slowly, you know, the longer it is, it's going at a slower rate. Decaying at a slower rate. Make sense?
Yeah.
Okay. Now, insert page after current. Okay. So that brings us to part D. Okay. So this one right here, we would say 0 for that one. Okay, so interpret the answer found in C. We know eventually, like we said, you know, it's eventually going to go down to C. If it keeps going down each time, and eventually it's going to come up to that. So it's going down to C. So usually a decay like that, even a half-life. You guys talk about half-life of like radiation and stuff like that. That is also a decay. Eventually, over a long enough time period, that will go down to 0. All right, so definition, horizontal asymptote right here. Graph of the function, okay? This one right here, so we have our function as it goes to negative infinity. This was a cotangent function. This is a arc cotangent, because we already did the, arc tangent, right? So this is an arc cotangent as it goes to negative infinity right here. This would be going to, what number we think this one would be? At least pi over 2. It looks symmetrical, so it looks like this go pi over 2 and this one negative pi over 2. But it looks like there's a shift also, because my interval for cotangent is from 0 to pi, where tangent is from negative pi over 2 to pi over 2. Okay, so right here I have the difference. So I have the lower asymptote, which they refer to as the M, and the upper asymptote right here for this. Make sense? Just my asymptotes. Okay, finding horizontal asymptotes of a graph. Now, for this one right here, what can I do for this one? Does it look like there's going to be an asymptote here? One, two, maybe? Okay, so now where I do this, okay, to find horizontal asymptotes is where I want to find where it's equal to 0 at. Okay, so for this one right here, I'll take the top. That one's not right. Okay, so sorry you people following along at home. Okay, this is the graph of the function that's actually on the slide right here. The graph is wrong, so I'm going to have to fix that. So this graph is wrong, so I'm going to have a asymptote, okay? It's going to go to a certain number, okay? So let's see where I'm at. Here I am. Okay, so this is not the right graph. So this is, bam, no. Okay, so for this one right here, okay, this one, as it goes to infinity, think about it. As it goes to infinity, what was the trick I showed you guys the other day? Is the degree the same, right?
And then you take the leading coefficients.
So it should be
3 over 4.
3 over 4, right? Okay, 3 over 4. Can I actually test that one? Can I test it? We just put it in the calculator, didn't we? Watch. Let's take a look. So for these, you have to put in numbers way over here. So let's take a look. So as I keep going, so let's go trace, graph, and let's start with, let's go 5. Okay, so, okay, it's going up. Let's go 20. Okay, looks like it's approaching that, right? So 2,000, 20,000, something like that. 0.75. It's getting so close to it that you're getting the number. But guess what? It's not going to actually be that. So it's never going to touch it because that's going to be a what? Say asymptote. Very good. So it's going to be an asymptote. So if you want to test it to see where it goes to, put in a huge number to see where it goes to on that number. Okay? All right. So let's take a look at the next.
So that's just to check. Using,
Yeah, that's a way to actually check. So 3 over 4, we did the trick, and there you go. But yeah, so sorry about the graph. All right, so finding asymptotes of the graph of the rational function. So first thing, I need to F that. Okay, how would I F this? Factor the top, right? Okay, what can I factor out of the top? 3 quantity x squared minus 4 over, now I need you guys to factor the bottom. Okay, I'm gonna factor the bottom for you. So it's 2x squared minus 4x minus 5x plus 10. So whichever factoring method you guys use, it's fine. You guys, some people like to do that little x thing. I still have never figured that one out.
Oh, I like
Okay. All right. So I just use a different method. So I use a different method to find this, just the center one. So I break it up and I can group it by parts. So factor by parts. So it's going to be a 2x quantity, x minus 2. I'm going to take out a negative 5, and I'm left with x minus 2. So it's x minus 2 and 2x minus 5. Okay. If you guys want, I can go over that again later. Okay. So yes, I did jump on that one. All right. So we have a 2x minus 5, and I have a x minus 2. Is there anything left that I could still factor?
Yeah. Difference of squares.
Difference of squares on the top, right? So difference of squares. So let's take a look. Difference of squares on here. So it's going to be 3x plus 2, x minus 2, over 2x minus 5, x minus 2, right? So I know I'm going to have some vertical asymptotes, right? Say yes. Okay, I'm going to have vertical asymptotes where? It's where the denominator is equal to 0, right? Okay. So where the denominator is equal to 0, I'm going to have some vertical asymptotes. But can I remove one of those?
Yes.
Okay, so when I remove it, what is it called? It's called a removable discontinuity. And what does it leave on my graph? It leaves a hole. It doesn't leave an asymptote, it leaves a hole. Okay, so that's going to leave a hole. So I know I'm going to have a hole where? Okay, so there's going to be a hole at x equals 2, right? There's a hole at x equals 2. All right, so now it's all done and all that, right? So now, let's take a look. I have another, where's my vertical asymptote? At x equals, remember, it's where the denominator is equal to 0. So this one's going to be, so now if you set this little piece right here equal to 0, yeah, it's going to be a positive 5 over 2, right? So positive 5 over 2. And so that's my vertical. What about my horizontal? What about my horizontal here? Is there an asymptote here? Yes, there is. Now, if I cancel this right here, right? Look at the coefficients right here. If I distribute that back in, do they have the same degree?
Yeah.
They have the same degree, right? So I'm going to have a horizontal at, oh wait, y equals, sorry. Does that make sense? Okay? We did a lot today, even though I promised you a homework day. Alright? Are we good? Okay. Alright, that's it. Okay, don't forget, like and subscribe, right?
Yes.
Okay, good. Hit that, what's that notification button, right?
Bell.